Hey everybody, so in our last lecture, we learned about bond polarity. We learned that depending on the electronegativity of the atoms in a bond, if one atom loves the electrons more than another, the electrons will shift towards the more electronegative atom, and that will make that bond polar. It'll make the more electronegative atom a little bit negative because the electrons have shifted in that direction, and it will make the less electronegative atom a little bit positive because the electrons have shifted away from that atom. Those areas of partial charge are known as dipoles. Now, unfortunately, there's one more wrinkle that we have to discuss, and that is that if a molecule has polar bonds, it does not necessarily mean that the entire molecule as a whole is polar. In other words, we can have situations where the shape of the molecule ends up negating the polarity of the bonds. And this is how that can happen. We're going to do a couple of bullet points, and then the examples should solidify this for you. If a molecule has a symmetrical shape, we'll talk about what symmetrical shape means in a little bit. If a molecule has a symmetrical shape, with identical terminal atoms, and thus the electrons are being pulled in equal and opposite directions, the polarity of the bonds cancels. And the molecule is non-polar overall. Now that's a lot to write down. I probably should have typed that. Okay, now you might need to pause here and go ahead and finish writing out that statement. But the easiest way to understand this, you guys, is with a few examples. So let's first look at carbon dioxide and water. So first let's look at carbon dioxide. Now we all know, after doing this a million times, that our Lewis dot diagram for carbon dioxide looks like this. And in terms of a molecular shape, we know with these two bonded domains, that is going to be a linear geometry, like so. Now what we need to look at, and if we wanted to label our atoms, here's my carbon, here's my oxygen, here's my oxygen. Now, what I would need to look at next is bond polarity. Okay, so we look at our Lewis structure, we look at our geometry, and then we look at bond polarity. We know that oxygen is more electronegative than carbon. So that means that the electrons in this double bond here on the right are going to get pulled out towards the oxygen because it's more electronegative. So that's a polar bond. But on the other side, we also have a polar bond, pulling in an equal and opposite direction. Now by equal, I mean equal magnitude. Like this is an oxygen and that's an oxygen. So the electronegativity differences on both sides of this molecule are the same. You would think that this would result in making this oxygen a little bit negative and the carbon a little bit positive. However, because these vectors are pulling in equal and opposite directions, they end up canceling one another out. So yes, this molecule does have polar bonds. These vectors cancel, and this is a non-polar molecule overall. The way that you could think about vectors canceling, I mean, you could just sort of eyeball it and see that those are going in equal and opposite directions. But if you remember from physics, we add vectors head to tail. So like if we were to have this vector, the one going to the right, and we add it to that vector, add vectors head to tail, back to the left. See how we ended up right where we started, right? The net result of the addition of those vectors would be 0. So because these vectors are pulling in equal and opposite directions, you're not going to end up with a net dipole. You end up net neutral, and you have a non-polar molecule. Let's look at another example where this does not happen. Let's look at water. We know water is polar, right? We did that whole lab where we did all of those cool things with water, seeing how polar it was. So I'm going to draw my Lewis dot structure sort of in the shape that I know the molecule is going to make. Remember, if you have 4 domains, you're in the tetrahedral family. And with those 2 lone pairs, we're going to call this shape bent. So here's my oxygen. Here's my hydrogen. And my hydrogen. So I look at my Lewis structure, and I look at my geometry. The next thing that I look at is the polarity of the bonds. We know that oxygen is more electronegative than hydrogen. So this bond right here is polar, pulling up towards the oxygen. The bond on the right is also polar, pulling up towards the oxygen. These 2 vectors are both pulling in the same direction. They're both pulling northwards, if we're thinking about a compass. Now, yes, one's sort of going to the right and one's going to the left, but besides the horizontal direction, there's also the vertical direction, and the vertical direction is the same. It's not canceling out. It's not like one is going north and one is going south. Right here, we had a clear east-west canceling of my vectors. Here, while one is going towards the left and one is going towards the right, they're both going upwards towards these lone pairs on the oxygen. These will not cancel out. If I were to add these vectors together head to tail, so like here's my first vector on the left, head to tail, other vector on the right, do you see how my net is up? Right? I get a net pulling up towards the oxygen. That's going to make these polar bonds remain polar. They are not going to cancel. This molecule has polar bonds just like the carbon dioxide one does. However, it results in a partial negative up here by the oxygen and partial positives down here by the hydrogen. This molecule is polar. So what I want you guys to see from this example, these 2 examples here, is that it's possible to have polar bonds and a non-polar molecule. Also, we can have polar bonds and a polar molecule where the polarity of the bonds does not cancel out. Now, of course, if your bonds are nonpolar, the molecule is nonpolar. Like, it's not possible to have a polar molecule unless you have polar bonds. So the scenario that we are considering this to be true is only when we have polar bonds present. You have to have polar bonds to have a polar molecule. But sometimes that polarity cancels out. And in order for that to be the case, you need this symmetrical shape and terminal atoms that are the same or that have the same electronegativity value. Let's look at another example. Let's look at carbon tetrachloride. This is going to be one of our tetrahedral geometries. So our ball and stick model. Will look like so. Let's look at the polarity of the bonds. Chlorine, more electronegative than carbon. All of these bonds are pulling in equal and opposite directions. They're all pulling at a 109.5 degree bond angle away from one another. This is a symmetrical shape. So even though we have polar bonds present, with this symmetrical shape, you will have a nonpolar molecule. And one final example, NH3. There's my Lewis structure. Trying to represent that pyramidal shape now with my ball and stick model. Next, we look at bond polarity. Nitrogen is more electronegative than hydrogen. The electrons are going to be pulled up towards the nitrogen. You see how all of these vectors are being pulled upwards? And oh, by the way, we've got that lone pair there on the nitrogen like we did with the oxygen and the water molecule. When all of these vectors are pulling in the same direction, they're not going to cancel out. They have to be going in opposite directions to cancel. So because they're all going in the same direction, these polar bonds will not cancel one another out. This molecule has polar bonds and is a polar molecule overall. Up here by the nitrogen, we're going to end up partially negative, and down here by the hydrogens, partially positive. Now, I suppose one last thing we should talk about here is what would happen if we had one of these symmetrical shapes like tetrahedral. But let's say all the terminal atoms weren't the same. Like, what if instead of a chlorine up there, what if we had a hydrogen? So here is where we're talking about the terminal atoms having to be the same. If this one bond was different, carbon is more electronegative than hydrogen. Do you see how we've just now added a vector in that downward direction as opposed to in the opposite direction? This molecule has polar bonds, but because all of the terminal atoms are not the same, because the vectors are not all going in equal and opposite directions, this will be a polar molecule. Overall, because of that hydrogen up there. So maybe the last thing that you guys should note is what are the symmetrical shapes? Okay, so our symmetrical shapes are 3-atom linear, trigonal planar, tetrahedral. Now, for those of you that did the extension, the pre-AP molecular geometries, there are some additional symmetrical shapes as well, specifically trigonal bipyramidal, octahedral, linear, square planar. We'll talk more about those next year in AP. But for now, you guys, these are your 3 symmetrical shapes. So if your terminal atoms are all the same in shapes that look like this, those vectors are going to cancel out. And so yes, you might have polar bonds, but the molecule overall will be nonpolar. And that is all she wrote. Now that we understand the polarity of different molecules, we are going to be able to look at the different intermolecular forces that are in play depending on whether or not a molecule is polar or nonpolar. Good job.